Alright, so my name's Lauren Moon. My presentation is on thin films in organic devices. There we go. Alright, so some background. How do these devices work? So, an organic semiconductor is the base device for a bunch of different kinds of devices. And they're built like this. You have the cathode, the emissive layer, the conductive layer, and then the anode. Now, these two layers are oftentimes in organic semiconductors, organic materials, and then the anode and the cathode are metal, which is why this interface here has some issues, because organic materials don't like binding to metal very well without change. So organic semiconductors aren't very good at being semiconductors without some modifications to the band gap, because organic materials have a big band gap, as you can kind of see here, because without modification, organic semiconductors act like insulators, but with modification, they will act like a semiconductor and the bands will be closer. So there's been some studies on how to modify the band gap in organic materials by oxidizing or reducing the layers. And there's been some studies on in situ tuning, which is you can tune the semiconductor band gap while it is being processed in solution. That way you can get the right amount of energy and it will do the function that you want. So the way band gap works is if it is a small enough amount of energy, said energy can be absorbed via photon or electricity, and then an electron will jump from the valence level to the conducting level, and then that in turn creates a hole in the valence level, and it is movement of these electrons and holes that creates current in said material. So this is dependent upon the quantum efficiency of a material, because if it isn't very efficient, then it'll absorb a lot of energy but not create as much current. And this is different than an insulator, because in an insulator, it'll take a lot of energy to promote an electron from the valence band to the conduction band. But in a quantum inefficient material, it'll just absorb a lot of energy but not produce very much current. So the electrons will absorb the energy, whereas here the electrons won't absorb such a low amount of energy, but they won't move around. The band gap size is what determines the material's electrical properties, like whether it behaves as an insulator or a semiconductor. So it's the band gap size that determines the material's electric properties, like whether it's a semiconductor, a conductor, or an insulator. So, more background. Some common materials used in organic thin layers are materials made of aromatic systems or polymer systems with conjugated pi bonds, like you can see here in rubene, and then acene, which is shown here in this molecule, this layer. Both of these are benzene rings in large aromatic structures. Sometimes these materials contain heteroatoms because that'll increase the conductivity and better binding. Like, once again, for example, in this paper, they used carboxylic acids, thiols, and amines to better bind with the metal layer, and then also that increases the conductivity of the material because those atoms are more electronegative than carbon. So you can add electron donating or withdrawing groups to the system, which increases the conductivity by increasing the mobility of electrons in the conduction layer or the mobility of holes within the valence layer. This is actually necessary in order to make a organic semiconductor. Otherwise, it would act more like an insulator because that band gap is so wide. So they have to dope it. So there's two types of conductors, N-type conductors and P-type conductors. N-type conductors are the ones that are doped with electron donating groups, and P-type conductors are ones that have been doped with electron withdrawing groups. Rubrene, here, this molecule, has a higher carrier mobility by about 2 to 3 magnitudes larger than acene-based compounds, and are considered the material with the highest hole mobility of all organic semiconductor materials. And fun fact, it is also the yellow light source in glow sticks. So, current and future applications of thin layers in this context where you're binding a metal layer to an organic layer for conductive purposes, are organic semiconductors, organic thin film transistors, and organic solar cells. Based on that, there's some common organic semiconductor devices: OLEDs, solar panels, and organic thin film transistors. So OLEDs are better than inorganic LEDs because they're less finicky and can be more flexible. Since lattice matching isn't as big of an issue, you don't have to have the atoms touching in a specific way, which is really helpful when you're making a flexible material, because when you flex a material, the atoms shift a little bit. And also, organic semiconductors are less crystalline, which makes them also more flexible. So an inorganic material is likely to be very crystalline, and if you bend it, it won't just snap. But organic semiconductors act more like plastics because they are more like plastics, since they have a lot of organic bonds that are more flexible. Organic solar panels are cost effective due to their solution-based production and low material costs. However, they have lower efficiency, stability, and strength compared to inorganic silicon solar cells. On the other hand, polymer solar cells are lightweight, making them suitable for small transportable devices. So some examples of OLEDs in action that we have now are folding phones and curved monitors. They're also beneficial because they have higher contrast. So if you think of your iPhone compared to your laptop, assuming you have a regular LED laptop, your iPhone has higher contrast and seems brighter and darker than a traditional laptop because of those OLEDs. Organic thin film field effect transistors, OTFTs, are less complex to fabricate compared to traditional inorganic transistors. OTFTs are promising in terms of materials and fabrication techniques and have been used in applications such as electronic paper, sensors, and memory devices. Although they have limited switching speed, OTFTs have a potential for a variety of future applications. So some current issues with the organic semiconductor materials include manufacturing-based problems, lattice matching and crystallinity, band gap, conductivity, and charge injection barrier, the failure to adhere, and degradation over time. So the most common methods, or so I've found, is magnetron sputtering deposition and thermal evaporation. The only problem is that these processes can damage layers and tend to permit metal penetration into the organic layer, which messes up the contact between the layers and makes spots of unequal electrical activity, and also creates weak points. So this creates flaws, as we will see. According to a 2021 paper out of Loyola Chicago, contact deposition routinely leads to thermal damage to the organic material and often penetrates through the organic layer. In other instances, metals fail to wet the organic surface, leading to a discontinuous film when thin metallic layers are needed for transparent contacts. Other prominent faults include contact delamination, charge injection barriers, and susceptibility to degradation. So contact delamination is when the organic layer slowly peels off of the anode or cathode, whatever is bonded to, and this creates flaking generally, and it just slowly ruins the semiconductor. Charge injection barriers are barriers to essentially injecting charges, so oxidizing or reducing that layer to increase its functionality as a semiconductor. And in this case, degradation can refer to slow oxidation of the material over time, or just breaking, like with the flaking off. So less commonly used is solution-based fabrication of organic semiconductor layers, which is imprecise, albeit easier than previously mentioned methods. It's currently the one that's used more for organic solar panels. There are two ways to address the previously mentioned problems: improve the materials or use additional layers. So you can either alter the materials making up the semiconductor or add a layer at the organic metallic interface that adds flexibility without hindering the conductive performance. By altering the makeup of existing components, you avoid potentially altering the band gap and retain the ability to tune the gap. But by using a thin film that binds to both, it reduces the damage from application and use. For example, it reduces the damage from like thermal evaporation, from contact-based application. So in the 2019 GWO study, researchers developed a flexible and semi-transparent organic transistor and circuit by using a polyphenylene oxide dielectric. The organic thin film transistor exhibited high mobility and mechanical bending stability, maintaining its electrical performance even after 5,000 times of bending. This development brings us closer to achieving high-performance flexible electronics. The rest of this presentation will cover recent studies on thin films in semiconductors for this purpose. This is a story in 3 parts. It all comes from the same group, the CISIC group at Loyola University in Chicago. I was momentarily an undergrad in that group. So the first paper is from 2013 in Chem about the functionalization of organic semiconductor crystals via the Diels-Alder reaction. So the synthesis scheme, this is the most important part of it because it's a Diels-Alder reaction, it's an organic reaction. So functionalizing the aromatic layer is helpful. Here they're using acetine, and it's helpful because it makes binding to other organic and metallic layers easier. As you can see, what they're doing is they're using the Diels-Alder reaction to add a bridgehead here, and then they did both acetine and rubrene. Then they added one of these heterocycles to that bridgehead to create a molecule. We'll see in a minute. And that makes it more electrically active and better at binding. Tetracene can have many different faces, many different orientations. This is relevant later. You can see that it comes out of the crystal face in a variety of different ways. In this way, it's coming out perpendicular to the crystal face. In this image, it's coming out parallel to the crystal face, and this impacts how it binds with other layers. So, second part of the story, a paper from 2019 from the CISIC group, also in ChemCom, about chemically transformed monolayers on acetine thin films for improved metal-organic interfaces. They further improved this layer functionalization of the previous Diels-Alder reaction of tetracene thin films to better direct adsorption of metal layers. In addition to the thiol product pictured here, that's a sulfur group. If you can't tell, it's bonded to the silver. They also did this with an amine substrate and a carboxylic acid substrate, and they synthesized and tested those as well. The way this reaction was carried out, according to the paper, monolayer transformations were induced by exposing the anhydride, this molecule, to water at 70 degrees for the carboxylic acid substrate, and butylamine at 40 degrees Celsius for the amine substrate, and cysteamine at 40 degrees Celsius for the thiol substrate pictured here. We can rationalize why this sulfur-silver bond would be stronger than a carbon-silver bond, and also a nitrogen-silver bond stronger than a carbon-silver bond, based on what we learned of the hard-soft ion principle. That explains why the functionalization of this molecule to here better adheres this organic layer to the silver cathode. So, in this paper, they also tested the durability to mechanical stress of these functionalized molecules. So, bending tests were performed by bending samples to a radius of 2.5 millimeters up to 100 times. So this is shown here. You can kind of see that the semiconductor is bent around a rod. You can see that the untreated samples here suffered significant delamination. They reported damage was noticeable after only 10 bending cycles and got progressively worse with more cycles until the 100 cycles were complete. The final product of that can be seen here. In the bottom row of images, they have the treated sample, which, as you can see, even after 100 bending cycles, has none of the flaking, cracking that you can see in the top image. These little dots are seeds of silver that you can, if the projector wasn't so blurry, you could see in this image as well. So that isn't a new thing. They withstood 100 bending runs. So the final piece of the story comes out of the CISIC group in 2021, published in the Chemistry of Materials journal. So all of this, what I previously talked about, culminates to the group's latest paper, which combines the previous elements to create self-assembled monolayers on the tetracene by reacting it with previously described Diels-Alder chemistry. This allows for better absorption of the silver layer, which makes the whole device more durable and also largely doesn't impact the quantum efficiency or conductivity of the material. You can see here that they did the same thing as in the last paper, in the sense that they made an anhydride and then reacted it with cysteamine, water, and N-butylamine, and then they used thermal deposition, so this is also a contact-based application, to apply the layer of silver for the cathode to the heteroatoms and to create these complexes. So the results of this paper are as follows. On the left, you can see the relatively large grain size of the silver layer and the depth to which it penetrates the untreated tetracene layer here. These shadowy parts are silver. This is the tetracene layer. This is silicon dioxide for the bottom of the semiconductor. And then on top is a mixture of aluminum, palladium, and platinum to make up the rest of the semiconductor. It's important to note that these observations are consistent regardless of the orientation of tetracene within the film. So remember, if tetracene is parallel to the film, it'll bind better than if it's perpendicular. They tested both parallel and perpendicular tetracene and had the same issues with grain size. The results are also in line with reported problems with thin electrodes, especially those in top emission OLEDs. So in the middle, you can see decreased grain size at the interface of the metal and organic layers, and how much smoother it is. You don't see as big of bumps like you do here. They're smoother, there's less variation, and how the thickness of the layer is more consistent, whereas here you have very thin parts like here, and right here you have a very thick part. Although it is not perfect, it still has bumps. It's still imprecise. You can see that here where there's a bit of silver that's been cut off, but you can see it dips quite deep into the organic layer, so this isn't a perfect method. The irregularity is more prevalent for perpendicular to surface tetracene compared to parallel to surface tetracene, since the upright conformation is less reactive to the Diels-Alder addition of the dienophiles, the functionalization of that layer. Although they have another paper on that as how defects in that layer does propagate the Diels-Alder reaction. On the right, you can see the comparative conductivity data and how a monolayer increases the electrical activity. Here is the treated tetracene, and this is the untreated tetracene, the pure tetracene. The treated tetracene, the self-assembling monolayer, has a higher conductivity than the pure tetracene, meaning that the functionalization is helpful in making the semiconductor conduct better. Yeah. So, in summary, to conclusion, there's a lot of variables in organic semiconductor design, such as the band gap and Fermi levels, movement of electrons and holes as the basis for current, the quantum efficiency of materials, and alterations of pi systems for organic materials by oxidation or reduction or doping. So there's a lot of different variables you can optimize in a semiconductor, like how well the metal can adhere to the surface of the organic layer, how small or large the band gap is, optimizing the conductivity of the material and the quantum efficiency. So there's drawbacks to the most common methods of fabricating semiconductors, the contact-based layer application methods. This method of creating semiconductors can damage the layers and impact the quantum efficiency, which is why thin films are a good solution to this problem. Functionalization at the surface of the organic layer can tune the band gap and help with the adsorption of both the metal and organic layers. A 2021 paper from the CISIC group at Loyola Chicago combined ideas outlined in previous papers to show that thiol, amine, and carboxylic acid-based self-assembling monolayers help adhesion at the metal-organic layer interface and makes the material more conductive, which makes the device more durable without sacrificing functionality. This makes organic semiconductor devices like organic solar panels and OLEDs more practical to use on a large scale. Okay, so references. I have 1 page of references. I have 2 pages of references, and then here's my acknowledgements. I made a collage. So this is Claire Underwood. She's my queen. I stand women's rights. I stand women's wrongs. This is Elizabeth McCord. She's also my queen. She is my president. This is Rebecca, also known as Hannah Waddingham from Ted Lasso. I love her. She's a girl boss. This is my favorite song right now. It's Care by Midwest. I've listened to it 20 times this week, and I guess it is already Friday. Anyway, this is Charles Leclerc. He's a Ferrari driver, and I'm obsessed with F1. I'm wearing a Ferrari jersey. This is Fernando Alonso. He's my favorite driver. He's so cool. He's so goofy. He's me if I could be free. I love this picture of him. It brings me so much joy. Okay, this is my mom. I love her. I couldn't be where I am without her. I love her. This is Chloe. She's my best friend. She's British, and she's not here right now. But she talked to me last night while I was writing this. Well, it was like 3 a.m. her time. I miss her a lot. I'm very excited to see her soon. This is me and my grad student. His name is Gaurav. He is the best. He's my mentor, technically, and probably my favorite member of the Berkowitz group. Love him to bits. So, yeah. Till next time. That's a really stupid thing to say. Is it? Should I just keep it?